All right, so in this lecture, I want to go through the Friedel-Crafts acylation reaction. This is a great reaction. It's another electrophilic aromatic substitution reaction. Okay, it has a single general mechanism for the most part. There's a little bit of a hitch there if you watch the lab movie, tiny one, but it's not as big of a deal as the alkylation reaction, and there's no weird rearrangements. Of the electrophile. For the most part, I'm sure there's somebody out there's found something, but nothing you need to worry about it for this class. Okay, so let's look at the reaction again. So what we're doing in the Friedel-Crafts acylation reaction is that we are reacting our arene with our benzene, with a molecule where the R group is attached to a carbonyl and then a Cl. This is called an acyl chloride or an acid chloride. The reason why we have that name will be clear during the last part of the semester. We'll talk about carboxylic acid derivatives and that sort of thing. So it's an acyl chloride or an acid chloride, and we're going to do a reaction with the same catalyst as the other Friedel-Crafts reactions. Now, instead of our benzene ring attacking or reacting directly at the R group, we're going to react at the carbonyl position. That's going to give us, oh, goodness no, the chlorine is gone, goes away with the catalyst. It's going to give us our R group attached to a carbonyl. Okay, so the mechanism, what you want to think about with this mechanism is it has a common intermediate. It has the acylium ion intermediate. So acylium is, first of all, a weird word, but it's got acyl. Acyl corresponds to our carbonyl. And ium responds to a positive charge. Whenever I have to remember, is it IUM or IDE that's positive, you think sodium chloride, sodium Na+, chloride Cl-. Okay, acylium ion. Now the acylium ion is an oxygen triple bonded to a carbon that's attached to the R group. I show that carbon as being linearized because it has a triple bond, right? And we put a plus charge onto the oxygen atom. Or you could draw it this way, where you've got a break between the triple bond and the single bond. That's designating where the carbon is. Or you could draw this as a resonance structure where the oxygen is double bonded to the C and the C is positively charged. Both of those are fine, but we have to remember the C is linearized because we cannot move nuclei. So the C is sp hybridized or linear in both of those resonance depictions. Okay, so that's our acylium ion. I'm getting that up in front of us front and center because that's the critical piece of the Friedel-Crafts acylation. Okay, so it turns out that in general, the acylation reaction is much more reliable than the alkylation reaction. You have a wide range of things that you can attach in the R group. You don't have to pay attention to the R group to do this chemistry. But let's go ahead and start with the methyl group. Okay, so we have benzene ring. I'm going to have a methyl group on my acyl group for my of my acyl chloride. React that with aluminum trichloride, and the product is going to be a benzene ring where I've replaced a hydrogen atom with a methyl group on an acyl group. This is called an acetyl group. We'll get to there in the final parts of the semester. Okay, Let's not worry about that right now. Now the mechanism for this, again, we're just going to highlight here, acylium. Most semesters I have to dock points on mechanistic proposals for this reaction and just write acylium because somebody's just completely avoided the acylium intermediate. Okay. So first step in an electrophilic aromatic substitution reaction is the electrophile. So the super electrophile in this case is the acylium ion. Now how does this work? Well, we're going to have our chlorine atom of our acyl chloride engage aluminum trichloride, just like we've done many times now. Lone pair of electrons, aluminum Lewis acid. That's going to give rise to this species. Positive charge in the chlorine atom that's on the acyl group. Now there's a few ways that you can approach this. My favorite way, because it gives us the best resonance depiction, is to let the lone pair of electrons, one lone pair on the oxygen atom, sweep down to make a third bond between carbon and oxygen and push the chlorine atom off. That's going to give rise to an oxygen triple bonded to carbon, which is then single bonded to a methyl group. The oxygen with only one lone pair of electrons is positively charged. It's group 6 element minus 3 bonds minus 2 electrons that are not shared gives us a +1 formal charge. But if you would rather just show the chlorine atom walking away directly, you would get this as a resonance structure. But you have to remember to draw that carbon with a linear bond between the carbon-oxygen and carbon-carbon. It needs to be linear at that central carbon atom. That's critical for accurate depiction of this strange intermediate, which is our acylium, the critical piece. So the acylium, it turns out, is our super electrophile. Okay, now everybody's going to be annoyed at me because I just made a big deal about how I want to see a carbon-oxygen triple bond. It's actually a little bit easier to see how the benzene atom, or benzene molecule reacts with our acylium using the one where the positive charge is at the carbon atom. Okay, I just say let's use 2 arrows. So the benzene is going to attack the linearized carbon of our acylium, and it's going to push the electrons onto the oxygen atom. That'll neutralize the positive charge on the oxygen atom, giving rise to an intermediate where we've got now a carbon-oxygen double bond, and we're back to a normal zigzag structure as the carbonyl carbon is back to sp2, so we can draw it as a normal trigonal planar structure as opposed to the sp hybridized requirement for our triply bonded structure. Okay. Attach there, put an H there, positive charge there. I've got the H at the carbon that accepted the acyl group. That tells me that when we form a, when we reestablish aromaticity, we'll lose that hydrogen, not any others, to give rise to our aromatic product. Okay, so there's our completed product. Now, alternatively, that's a good mechanism. That's the mechanism I would propose. Okay. Alternatively, if you want to show the linearized acylium ion with a positive charge in the carbon atom, just a different resonance depiction, you don't need that second arrow. You can just draw one arrow, but it might be a little bit easier to see why the positive, why the carbon atom gets attacked. It's the one with the positive charge. It's going to give rise to the exact same intermediate, which will give rise to the exact same product, because when you use mechanisms with resonance structures, you get the same outcome. Just may have to use a different number of curly arrows to get there. Okay, so that's the Friedel-Crafts acylation reaction. Turns out that it doesn't matter what's attached to that acyl group. It could be benzene, it could be another benzene if you wanted it to be. So let's say we've got benzene and we react it with an acyl chloride where the R group is the most horribly drawn benzene ever, sorry. I really want to write pH for abbreviation for the phenyl group where benzene is a substituent, but you get it. In this case, the product is going to be our acylated benzene plus the R group that came along with the acyl group. In that case, it's just benzene. The mechanism is the exact same, so the mechanism uses a different acylium ion in this case, but it's otherwise the same. Go here, plus aluminum trichloride. So the resulting aluminum with the negative charge puts a positive charge in the chlorine atom. You could let that chlorine walk away just like this and put the positive charge at the central carbon, but you need to have that linearized. I like to have a lone pair coming down to remind me that I've got a triple bond, so I need to keep that linear. So I'm going to have my molecule sitting off this way. The aluminum Cl4 goes ahead and breaks down to aluminum Cl3 to turn over our catalyst. Okay, benzene is going to recognize an opportunity at that central carbon atom. Attacks there, pushes the electrons up. It's going to give rise to this intermediate. You'll notice I'm just drawing the exact same mechanism, but I've got a benzene atom, benzene ring on one side of the acyl group, on both sides, excuse me, as opposed to just one side, because I replaced that methyl group with a benzene group. My point is I can change the R group that's on the acyl group to anything, okay? The R on our acyl group can be anything. It doesn't matter. The mechanism doesn't change. It's just comes along for the ride. Okay. So that's the Friedel-Crafts acylation reaction. Mechanism doesn't change with the R group. Make sure you understand the acylium ion. This is a super important reaction. I will ask you a lot of questions about it. But otherwise, that'll sort of do it for this reaction, this reaction and this lecture. So we'll move on to some more reactions of benzene in future lectures. Until then, I'll see you.